In the previous section, we talked about what makes water unique and what potable means. So why is fresh water, potable water, so hard to find? This is because it makes for such a great solvent. Water is able to dissolve in a great variety of substances to create solutions. A solution is a homogeneous mixture of uniform composition. This means that it can mix together with something else and have the substance completely spread out. So if you make salt water, the salt will be distributed throughout the glass of water. Solutions are made up of solvents, which is the substance that is dissolving the particles, and the solute, which is what is being dissolved. There is usually more solvent than solute in a solution. So if we look at salt water, salt is the solute, while the water is the solvent, which is what's doing the dissolving. When water is the solvent, it's called an aqueous solution. Since water is such a good solvent, it's practically never 100% pure. The concentration terms for solutions are the same as those that we discussed earlier in the beginning of the semester when we talked about gases. For instance, a percentage is still parts per 100. Parts per million is still how many solute particles are in every 1 million total solution particles. And parts per billion are still the number of solute particles in every 1 billion total solution particles. A term that we haven't discussed yet, however, is molarity. Each element has its own weight. Earlier in the chapter, I mentioned that water is 18 grams per mole. Notice the unit mole. Each element has its own weight because it has different numbers of protons and neutrons, which make up the atom. A mole, you may remember, is if we counted every single one of these atoms or every single one of these molecules. So 1 mole is the same as 6.02 times 10 to the 23rd particles, which is 602 particles. So that we can focus on particle solutes rather than the weight of it, chemists use the unit mole and subsequently molarity. Molarity is the number of moles in 1 liter of solution. It's a way to consider the mass, but keep everything on the same playing field because we're talking about particles instead. You may remember sometime in your life being at a swimming pool and the lifeguard telling everyone to get out of the water because the lightning was seen. This is because chlorinated water conducts electricity. In order to conduct electricity, electrons must be able to move from one location to another. Some solutions have the ability to do this while others do not. Electrolytes conduct electricity while non-electrolytes do not. You may have heard the word electrolyte before in Gatorade commercials. There are charged particles such as salt in Gatorade, which is why it conducts electricity. In order for solutions to conduct electricity, it needs to have some charged particles floating inside of it to carry the electrons around. Ions are these charged particles. An ion is an atom that has either lost or gained electrons. This slide is an example of ions that you're undoubtedly familiar with. Sodium here wants to lose one electron, and when it does so, you're subtracting a negative. You're minusing a -1. That turns out to be a positive. So sodium becomes a +1 charge. Chlorine, however, wants to gain an electron, so you're gaining a -1. So it becomes a negative charged. The positively charged ions are called cations, while the negatively charged ions are anions. These two come together to make sodium chloride, which is actually table salt. When they come together, one gives up an electron, one takes an electron, so they both end up happy and getting what they want. Remember that this is once again another picture of the periodic table. You may remember that the groups, or the vertical columns, are families and they react similarly. They react the same because the electrons generally behave in the same way. Notice where sodium is on the periodic table. It's on the far left. It's the first row. Notice that each one of these atoms in the first row have a +1 charge. This is because they all need to lose one electron in order to be like the noble gases on the far right, which are the most stable of all and do not want to react in general. All the elements on the periodic table want to be like them, and they're going to lose or gain electrons in the quickest way possible in order to do that. If we look here, if we took a step backwards, if they lost electrons, they would be like the noble gases. Now look at where chlorine is. If we go the other direction and we gain an electron, it will be like the noble gases. This creates a definite pattern on the periodic table. All the atoms in row 1 all have to lose one electron, so they all become a +1 charge. Row 2 needs to lose 2 electrons to be like the noble gases. If you go on the other side of the periodic table, fluorine, chlorine, and bromine are one row away as well, but in the other direction. Meaning they have to gain an electron, and so they become a -1. Oxygen and sulfur need to gain 2 electrons. They need to move 2 spots. And row 5A needs to move 3 spots to be like the noble gases. So let's move on to actually naming the compounds. Naming simple ionic compounds are actually pretty easy. Name the metallic element first, which is the cation, and then name the non-metallic element, which is the anion, second. With the anion, you're going to change the ending to "ide." An example here is MgO. Mg is magnesium, while O is oxygen. Magnesium is the metal, oxygen is the nonmetal. So we change oxygen to oxide, and it becomes magnesium oxide. Another example is sodium and bromine. Na is sodium, Br is bromine, Na is the metal, Br is the nonmetal, so sodium is the metal, bromine is the nonmetal. Bromine becomes bromide to become sodium bromide. This is a list of polyatomic ions. If we break down the word polyatomic, we have poly, which means many, and atoms, atomic, referring to the atoms. So we have an ion that has many atoms. If we look here, sulfate, it's right here, has 1 sulfur and 4 oxygen. Here's the sulfur with the 4 oxygens. all combined together have a -2 charge. So there's many atoms with one charge. Naming these are also easy because they're very similar. We have magnesium, and then OH here is hydroxide. So Mg is a cation, hydroxide is an anion, so it becomes magnesium hydroxide. NH4 is ammonium, where Br is bromine. Just like with the other ones, instead of I and E, we're going to change that to ide. Ammonium is a cation, bromine is an anion, so it becomes ammonium bromide. So let's go back to the electrolyte concept. Remember, electrolytes conduct electricity because they are able to carry a charge from one location to another. Substances will disassociate, which basically means break apart, in a solution called electrolytes. The polar water molecules stabilize the ions as they break apart. We talked earlier about how oxygen is more electronegative than hydrogen. As a result, the electrons drift towards the oxygen and away from the hydrogen. This leaves oxygen more negative and the hydrogen more positive. You may also already know that opposites attract. So the negative parts of the water are attracted to the positive ion or cation, which is sodium here. The positive parts of the water, which is the hydrogen, are being attracted to the negative ion here, which is chlorine. The breakdown and attraction of these ions is how the charges are able to float around. A sucrose molecule, when dissolved in water, sugar molecules interact with and become surrounded by the water molecules. But the sucrose molecules themselves do not dissociate. They don't break down like the ionic compounds do. So covalent molecules remain intact when dissolved in water. Since there's no charge, because there's no breakdown, sugar does not conduct electricity, so it's not an electrolyte. So let's talk about what does dissolve and what doesn't dissolve. In order for two things to dissolve and mix with one another, they need to be similar. This picture has a beaker that contains both oil and water. In the previous slide, I discussed how the positive and negative ions interact with water, while oil doesn't have these positive and negative ends, so it doesn't get a chance to mix with the water. Even the sugar had some negative areas where the oxygen were located. Oil, however, do not have any areas like this. Luckily, there are things called surfactants these molecules that have charged area and a non-charged area. This means that the oils, like the ones on our skin, can interact with the non-charged areas, and then the charged areas can interact with water. So surfactants have both charged and non-charged. And this is an example of this is soap. But in order to work properly, it needs to have both charged and non-charged sides. The charged particles work with the water, while the non-charged work with the oil. Now that we know how things are dissolved in water, let's take a look at what's in our drinking water. The safety of our drinking water is dependent on what the contaminant is and its concentration. In 1974, the Safe Drinking Water Act was put into effect to ensure that our tap water is safe to drink. What you see on this slide is a small list of contaminants in our drinking supply that is regulated by the Environmental Protection Agency, the EPA. There are actually 80 contaminants that are regulated, so this is only a few of them. The maximum contaminant level goal, which is right here, the MCLG, is the quantity of contaminant in which no known or anticipated adverse effects on human health would occur. If you did not catch that definition, it's on page 227 in your text. If an average person weighed 154 pounds were to drink 2 liters of these substances for 70 years, would have no effect. Please realize that this is not a legal limit, but a goal we are striving for. So these are goals. Notice that some of them actually say 0. This means that we would like to get to the point where there's none of these contaminants. The maximum contaminant level here, on the other hand, is the legal limit. If the concentrations of any of these contaminants go above these concentrations, legal actions could occur. So notice that on one angle it says 0, but the other one 0.005. 0 is what we would like. 0.005 is acceptable. Notice that the difference between the two, the goal is 0, but legally they are allowed to be some in the water. On the other slide, you see typical steps for water treatment. On this slide, you see typical steps for water treatment. It starts with the water source. Around Northwest Indiana and Chicago, most of our water comes from Lake Michigan. The water is pumped up and passed through screens to get rid of the bigger items like weeds, sticks, and trash. The aluminum sulfate and calcium hydroxide is added to the water and passes through a fluctuator to get rid of the smaller debris like clay and dirt. The water is then passed through the settling grate tank and through coal or charcoal, gravel, and sand to get rid of anything that did not settle out. Bacteria in the water is killed by chlorination. The majority of the chlorine is then removed, but an extremely small amount remains to continue to protect the water from the threat of bacteria returning. Some people worry about the chlorination process, but prior to this, thousands have died by the result of bacteria in the water. So it's the lesser of two evils. Most cities then add fluorine to the water to protect against tooth decay. And then it's stored in the water towers and then moved to the cities. When fresh water is not available, some cities choose to go through steps of desalination. This is a process that removes ions from salt water. Even though the earth is 3/4 water, most of it cannot be consumed. This process makes the seawater acceptable to drink. So this process is called desalinization. One way of getting the salt out of the water is through distillation. Distillation is the separation process in which liquid solution is heated and the vapors are condensed and collected. Water is heated. In doing so, the water is turned into steam and leaves the container. Impurities remain at the bottom of the boiling container. Unfortunately, it takes a lot of energy to do this. So notice here is another way. That's just an energy source. Another way to remove salt of seawater is osmosis. Osmosis is the passage of water through semi-permeable membrane from a solution that is less concentrated to a solution that is more concentrated. A semi-permeable membrane means that there are tiny little holes that only a few substances can fit through, such as water. So what happens is that one side of the membrane has a very high concentration, so a lot of salt, and on the other side has very little salt. They actually use it as reverse osmosis. In regular osmosis, the molecules will try to even out the concentrations. In doing this, the water would actually drift towards the pollution rather than away from it, so this won't work. This is why we perform reverse osmosis. Reverse osmosis uses pressure to force the molecules of water through the semipermeable membrane from the solution from the more concentration to the less concentration. So you're removing it from the solution, not pollution, not adding it to the pollution. The water doesn't want to do this naturally, so it has to be forced into separating out. One way that's been developed for countries that are having a big issue is the life straw. It's another method to filter out water. It is created for developing countries to remove bacteria, viruses, and parasites from water to make it drinkable. It's not a permanent solution. Some contaminants still get through, but it is much better than nothing at all. It's odd to think that the most abundant natural resources we have can also be the most scarce. Fortunately, in the U.S., we don't have such a huge problem with this, although some areas do. We must never forget that we're actually very privileged.